Well, we've been working in section 4.3, which is about primes, greatest common divisors. At least that's the title of the section. We do quite a bit more in here. We want to throw out a new definition out there. It says, two integers a and b are said to be relatively prime, provided their greatest common divisor is 1. So two integers are relatively prime if the largest thing they have in common is 1. The largest positive integer in common is 1. That is, a and b have no prime factor. So that's equivalent to saying a and b have no common prime factor. So we want to do a little bit with this concept of relatively prime. We want to introduce a very famous function known as the Euler Totient function. So Leonhard Euler was a famous mathematician in the 1700s. He's from Switzerland, and he went around Europe and he did quite a bit mathematically. He was very able to go among different branches of mathematics. He wasn't specialized in just one branch, but he did a great deal from calculus to number theory to astronomy. And he's probably one of the most prolific mathematicians of all time. So he introduced this function that we call the Euler Totient function. We used the Greek letter phi, or actually it said phi in Greek, but a lot of times you'll hear it called phi here in the US. So we're going to say phi or phi of n. The idea is you have a positive integer n, and you want to calculate phi of n. What phi of n calculates is the number of positive integers that are relatively prime to n. So it's the number of positive integers relatively prime to n that are less than n. So the number of positive integers relatively prime, if I can spell relatively, to n, that are not less than or equal to less than n, that are less than n. Less than n, so they have to be smaller than n. So everything that's relatively prime to n, and that's also less than n. Now let's do some examples. Exercises. Number 1, we want to compute phi of n, okay, for different values of n. So number 1, we want to calculate phi of 3. So here our n is 3. So here at the bottom, I'm going to list those positive integers that are relatively prime to n and less than n, so less than 3. Relatively prime. Can I spell prime? Maybe I'll make a little column here. I'll say relatively prime to n and less than n. So in this case, we're talking about n equals 3. And we want them to be less than 3. Yeah. Relatively prime to 3 and less than 3. Okay, I'll just leave it up there. So what's relatively prime to 3 and less than 3? So 1 is relatively prime to 3, right? 1 and 3 have nothing in common except 1. And also 2 and 3 have nothing in common except for 1. We don't include 3 because 3 is not less than 3, so it has to be less than 3, so only 1 and 2. So there are 2 values here. So phi of 3 is equal to 2, right? All right, let's do a number 2. Let's find phi of 4. So what's relatively prime to 4 and less than 4? Well, 1 is, 2 is not, because 2 and 4 have a 2 in common. Is 3 relatively prime to 4? Yeah, right. 3 and 4 only have a 1 in common. And that's where we stop, right? We stop at 3. We always stop below 4. So that's 2 values again. 1 and 3 are relatively prime to 4 and less than 4. All right, number 3. Phi of 5. All right, so that's going to be 1, 2, 3, and 4, right? 1, 2, 3, 4. All have only a 1 in common with 5. That's 4 values. All right, number 4. How about phi of 6? 1. 2 is not relatively prime to 6, right? 2 and 6 have a 2 in common. 3 is not relatively prime to 6, because 3 and 6 have a 3 in common. 4 is not relatively prime to 6, because there's a 2 in common. 5 is, right? 5 and 6 have just 1 in common. So just 2 values. Phi of 6 is 2. Let's do phi of 7. Let's see, 1, 2, 3, 4, 5, and 6 only just have 1 in common with 7, so that's 6 values. Phi of 7 is 6. So let's do phi of 8. Phi of 8, let's see, 1, not 2, because 2 and 8 have a 2 in common. 3, not 4, because 4 and 8 have a 2 in common. 5, not 6, because 6 and 8 have a 2 in common. 7, and that's it. 1, 3, 5, and 7 are relatively prime to 8, so that's 4 values. Phi of 8 is 4. So something you might notice here is when we have phi of a prime, here's a little fact. Phi of a prime p is going to be p minus 1. This is when p is prime. So phi of p is easy to calculate when p is prime. Let's look at that. So remember, when you have a prime 3, you get an output of 2, right? When you have a prime of 5, you have an output of 4. When you have a prime of 7, you have an output of 6. And that makes sense, because every positive integer below a prime is going to be relatively prime to that prime. Why? Because a prime should not have anything in common with any other numbers except 1. Okay, so phi of p is easy to calculate. Now when you look at phi of 4, you get 2. Phi of 6, you get 2. Phi of 8, you get 4. There's really no apparent pattern here, maybe if you look at this. But what we want to do, we want to give you a formula for finding formula for phi of n in general. And it goes like this. If n, remember n's a positive integer, is factored into a prime power factorization p1, alpha 1, p2, alpha 2 through pk alpha k. Remember, the pi's are prime, and the alpha i's, I'll just say the alpha I are greater than or equal to, well, let's just say are positive integers. And then here's the formula. Phi of n, the way you calculate that, you take the number n, you take 1 minus 1 over p1, that's your first prime, 1 minus 1 over p2, and so on, 1 minus 1 over pk. You do that for each of your primes. Now the exponents have no bearing on this formula. It really doesn't matter what the exponents are. They don't come into play here. It's just n times 1 minus 1 over your first prime times 1 minus 1 over your second prime, so on and so forth. 1 minus 1 over your last prime. Those multiplied together. So let's say we wanted to find phi of 1,000. So phi of 1,000, how many positive integers are relatively prime to 1,000 and less than 1,000 at the same time? Well, if you wanted to list all those out, it would take forever. You'd probably miss some, make some mistakes. We're just going to use our formula. So let's think about what 1,000 is. 1,000 is, we're going to do a prime factor tree on 1,000. Let's do 1,000 here. 1,000 is 10 times 10 times 10, right? And the 10s break down into 2 times 5, those are primes. 2 times 5, those are primes, and 2 times 5, those are primes. So I'm counting up the 2's. So I have 1,000 here. Let's write 1,000, that's my n, is what? 2 to the third power times, we have 3 5s, 3 copies of 5, so 5 to the third. So 2 to the third times 5 to the third. So if I'm calculating phi of 1,000, I have to start off with my n, which is 1,000, times 1 minus 1 over my first prime. My first prime base here is 2. And then 1 minus 1 over my second prime here, which is 5. So we're talking about phi of 1,000 is 1,000 times 1 minus a half is 1/2. 1 minus a fifth is 4/5. Let's see, if I multiply here the tops, 1,000 times 1 times 4, I'm going to get 4,000. And if I multiply my bottoms, 2 times 5 is 10. So 4,000 over 10 is 400. So my answer is 400. Phi of 1,000 is 400. There are 400 positive integers relatively prime to 1,000 that are less than 1,000. So that's a handy formula to have. Now, if you want to go back, you could actually check all of these. So remember we counted up the number that were relatively prime to each value of n back here, and that were less than n. Let's say we wanted to use the formula. Here's the formula. We would have started with our n and number 1, which was 3, and then multiplied by 1 minus 1/3. Because the only prime for 3 is 3 itself. So 3 times 1 minus 1/3, which would be 3 times 2/3. The 3's cancel and you get a 2. And right, that's exactly what we had back there. Now, when you're dealing with phi of 4, so here you have n. So the value of n here is, so the first one was n equals 3. The next one is n equals 4, and we know 4 is 2 squared. So our only prime here is going to be 2. So when we're calculating phi of 4, okay, let me actually write it out. If I can write this. First one was phi of 3. This next one is phi of 4. You start off with your n, which is 4, and then you have to multiply by 1 minus 1 over 2, right? Because our only prime in 4 is 2. So you get 4 times a half, which is 2. And that checks out. Then we go on to n equals 5. 5 is a prime, so we'll do phi of 5. We got n, which is 5, times 1 minus 1/5. Our prime is 5 here. So we have 5 times 4/5. The 5's cancel and you get 4, and that checks out. See, when n is 6, we would find what phi of 6 is. Now remember, 6 is actually 2 times 3 in the prime factorization. So I'm going to have to start off with n, which is 6, times 1 minus 1 over 2, times 1 minus 1 over 3, which will be 6 times a half times 2/3. So you're going to get on top 6 times 1 times 2 is 12. On bottom, 2 times 3 is 6. So 12 over 6 is going to be 2, which matches number 4. Okay, and number 5, we have n equals 7. 7 is a prime already, so we don't need to factor it. Phi of 7 would be n, which is 7 times 1 minus 1 over r prime 7. In other words, 7 times 6 over 7. 7's cancel, you get a 6. Checks with number 5. Now let's do number 6, phi of 8. Remember, n is 8 here, which is actually 2 to the 3rd power. We have a n is 8. So phi of 8 is 8 times 1 minus 1 over r prime 2. So you got 8 times a half, which is 4. And that checks with numbers. That's number 6 right there. Okay, so that's called the Euler Totient function. So something else we want to introduce is the concept of pairwise relatively prime. So here's a definition. The integers, so here we're going to actually have a list of integers, several integers, a1, a2, and so on and so forth through an. These integers are pairwise I don't know what happened there. Relatively prime. Sorry about that. Pairwise relatively prime. Provided the GCD of each AI and AJ equals 1 for all I less than or equal to, sorry, I greater than or equal to 1, I less than j, and j less than or equal to n. So what this is saying that none of the pairs of the integers have a prime in common. None of the pairs of the integers have a prime in common. That's what that's saying. So let's look at some examples to determine if things are pairwise relatively prime. Determine if the integers are pairwise relatively prime. So I'm going to give us 3 integers, 9, 10, and 17. And basically we're going to look at these in pairs. I'm going to take 2 at a time. So I'm going to look at 9 and 10. Okay, those are relatively prime. Then I'll look at 10 and 17. That pair is relatively prime, right? They have no pair in common, no prime in common. Then I'll look at 9 and 17. They have no prime in common, so yes. Yes, the integers are pairwise relatively prime. All right, let's do number 2. We have 11, 14, and 169. Achoo! Excuse me. That's a sneeze right there. Look at this in pairs. I'll start with my 11 and 14. They have no prime in common. 14 and 169 have no prime in common, and 11 and 169 have no prime in common. So yes, these are pairwise relatively prime. So yes, the integers are pairwise relatively prime. Number 3, we do 13, 14, 15, 19, and 21. And the answer is going to be no, these are not pairwise relatively prime. There are actually 2 reasons. Number 1, when I look at 14 and 21 as a pair, they have a greatest common divisor of 3. They have a 3 in common. I'm sorry, 7. 7. And also, when I look at 15 and 21, they have something in common. They're the ones with the 3. Okay, yeah, 15 and 21 have a 3 in common. So no, they're not pairwise relatively prime. There's some primes in common between different pairs. All right, so that's it for this video. In the next video, we're going to look at, well, something known as the Euclidean algorithm, and we're going to use that to solve